Hello everyone, this is Intro to PV Snow Day. So I have a couple of videos here for you that hopefully work out. We're going to go through the lecture that we would have had last week and a little bit of what we had for this week, and in preparation that we would just go right into calculations for next week. Um, so some of this stuff we've talked about. Some of the stuff I want to go into greater depth right now, and some of the stuff I don't, or we already have. So a little bit of it will be review, some of it won't be. Okay, here we go. So we have a renewable energy system. We could take a look at this, and you should see batteries, you should see a solar array, you should see the utility, and immediately off the top of your head you should say multimodal. Yes, indeed. So we have all sorts of different system types. Here's some schematics or visualizations of things we have talked about presented in a different way. So here's a utility intertie system. Here we have the grid coming into a service meter, a service panel. Out of the service panel, we have a breaker connected to an inverter that's connected to an array. So we're going to generate DC electricity. The inverter is going to interact with the utility and our electrical infrastructure and create a artificial sine wave that is of a certain voltage and a certain frequency that will be compatible for the utility. So these renewable energy systems, they'll have a bidirectional meter or a double meter, a dual metering system. A bidirectional meter will clock up production and consumption, and at the end of the month you get the net reading. So either the utility owes you or you owe the utility. It doesn't tell you how much you've consumed, only how much you owe or they owe. On a dual meter system, we're going to sell everything from the PV array to the grid through one meter and bring it back in through a utility grid meter. So everything is sold, everything is bought. So we know how much is produced, we know how much is consumed. And there's a few utilities like that. I'm aware of one in our jurisdiction, or one in our area, service area, territory, that we have that. In a net metering scenario, this is a single bidirectional meter that has to be set up by the utility. This is a special meter. If it's a digital one, more of a smart meter like we have in ComEd territory, or most of ComEd, you would see that taken care of from their HQ. Nobody comes out. So anyway, so when we produce electricity, DC electricity off the array, goes to the inverter, creating a utility grade electrical that feeds our loads. Any excess goes out to the grid through the utility meter, clocking up a credit. And when we're not supplying enough power from the PV array, we buy back those credits or buy from the utility. Dual meter, again, like I said before, everything is sold to the utility and then everything is bought from the utility on a separate meter. And that works out for a little bit better accounting. You know exactly how much you produce. You know exactly how much you consume, which you don't have on a net meter or bidirectional meter system. We've talked about distributed generation before on day one. Distributed generation is generation on site where it's used or very close to that. We don't have this long distribution system that is required for central generation. These days we have massive utility scale operations going in as we speak, but we also have these community solar projects in this state. Not every state will allow that to happen, But here in Illinois, you have that ability. So what that means is that if you can't afford to install solar on your house, or it's not appropriate to be there, it's too shaded, or you don't have enough space, or you're a renter, you buy into this community solar project, you buy a share of that, say, I don't know, whatever you can afford, maybe 4 panels or 8 panels or 6 panels, whatever that might be. And whatever those panels produce, you're credited on your utility bill for that. So that works out really nice. So even if you move, that stays on your bill as you move around, whether you be a renter or a homeowner that's going to be at a place only temporarily. Each state has what's called a renewable energy portfolio, or RPS, and these RPSs are legislated goals for the state. For instance, the goal of Illinois is to have 100% renewable energy by 2050, and I believe 50% by 2030. So goals for install of renewable energy systems, and sometimes that the state may incentivize that, sometimes they may not. So it's a political goal to do X amount of kilowatts of renewables. That would include solar, wind, maybe some hydro, biomass, all the above. Just a small tour of different types of remote or portable systems that you may see out on the road. We have certainly off-grid systems that will power something like a billboard or a bus stop. No connection to the grid to a whole home or more. We have remote monitoring. Lots of weather monitoring and traffic monitoring is done through these sensors that are powered by renewable energy, a small solar panel. Here we have a water pumping system, or an array, out in the back 40. We have a deep well pump. The array powers up the pump fills up the stock tank, and a float switch will turn on and turn off the pump. So when the stock tank is full, pump turns off, and the cattle come, suck it down, then it'll turn back on. And then at nighttime, the system doesn't have any power because the sun is down, and it's PV direct. So when it only operates when the sun is shining, so during the daylight hours. At nighttime, the battery, if you will be this reservoir of water, this stock tank that's full of water that will tide the cattle over until daylight. We also have portable systems. A big market for small systems are RVs. RVs already have a battery system, and an inverter. So they'll pull into a RV site, plug in, charge up those batteries, and then live off those batteries to run appliances in the RV. Well, you can simply incorporate a few solar panels, which are fixed to the roof, whether they be amorphous or crystalline cells, and integrate right into the charging system of the battery pack on the RV, and you don't have to plug in. Then you can have power all the time and not be reliant on having to plug in. More and more, we see more and more highway construction signs on the interstate, which are not powered by gas generators anymore, but by solar. So they're charging up a battery pack to run the digital sign. And then remote locations, whether that be for communications or exploration and research or whatever that might be, they're going to use renewables to roll out and power up communications or research equipment. There's a couple of different types of systems that we haven't talked about, and I just want to bring them to your attention. One of those is the direct use battery-based system. So I have a load here, and that load is going to determine the battery size, and the battery size is going to determine the array size. So nothing new there, but what happens is, like on navigation buoys in the water, you'll have a light strobing, and or a constant light, and the battery is sized for the duration of that light being on during the evening, and then the array is sized to meet the battery's needs to fill up that battery during the day. So it's a really closely sized system, so the battery will be depleted or nearly depleted by sunup, and then the array has to be large enough to power up that battery throughout the day. So the reason for this tight parameters is that for weight and expense. So the battery is just enough to power up the light during the evening time, and the array is sized to power up the battery during the day, just enough. The speed sign that's out on the roadway coming into campus, that's what you see here. That's a DC-based system, has a single panel, a charge controller, a lithium battery, and a DC load, the speed sign, and electronics. So there is no inverter on that system. In this neck of the woods, we need to have if we have an off-grid system, we need to have a generator to get through the low sun hour months, December, January, February. When I had a system, this is very similar to what I had to be able to, I had to get out the generator around Christmas and Valentine's. During that time period where I lived, we had this low light, no wind, like ice fog that would come in for a week or so at that time period. So in an off-grid system, that inverter is going to be able to operate independent of the utility, because there is no utility, and operate off a low voltage battery pack. But then it also has to be able to charge. So this is an inverter charger. So I hook the generator up to the inverter and run that for a couple hours, and it'll top off the batteries. So this is a more sophisticated inverter than, say, a multimodal inverter. That's sophisticated too. But this one is an inverter and also a charger. Hybrid systems, we talked about this, I believe. Yes, we did. We have an array of PV. We have wind generator. They both feed into a common battery pack, and then out of that battery pack into an inverter, and then to the AC loads. So sizing of these types of systems, we're going to take the annual load of the home and run half of that with PV, half of that with wind. So in the spring, summer, early fall, when we have the sun resource, the PV is going to be our primary power source. In the late fall, winter, early spring, the wind generator is going to be our primary source of electricity. Multi-mode systems, we talked about these. We have an inverter that can operate standalone as well as with the utility. We have battery backup on site for meeting loads that are needed, and those loads, critical loads, are running 24 hours a day, whether the grid is present or not. Now, these multi-mode systems have traditionally been lead-acid battery-based systems, just like these standalone systems, but now we're moving into an era of lithium-ion batteries. Panasonic, LG Chem, Tesla, and a handful of others who are moving into that realm. Many of the systems that we install at Full Spectrum Solar are battery ready. we do install a number of battery-based systems throughout the year, but we install many more systems that are battery ready, meaning that we put in the array, we put in the inverter, we connect it to the grid, and it operates in a grid-based fashion. However, it has the ability, when the homeowner is ready to pull the trigger, to add batteries to for critical needs. So that we can do battery-ready systems where we couldn't do that 5 years ago. So we have this DC made off of the array, and then we have an inverter which inverts that to usable AC. And in a minute we'll talk about how it does it, but it's based on transistors that are in high-speed switching that are going to create an artificial sine wave that's actually smoother and cleaner than what the utility can provide. We have inverters that change AC into DC, and that would be a rectifier. So we have an inverter charger or inverter rectifier type system. When we do that, these rectifiers use diodes to cut half of the sine wave in half, and then the opposite direction flips that sine wave into the upper layer, the positive side of the zero line, so that we have a constant pulse of DC. So we're converting that AC into a DC signal, flattening it out into a constant voltage and current output. And that's with diodes. We talked a little bit about solar irradiance and how we measure that. We measure that in meters per watts per meter squared. And at sea level, on a clear, crisp day, ideally we would see 1,000 watts per meter squared. Outside the atmosphere of the planet, we have a thing called the solar constant. That solar constant is 1,366 watts per meter squared. So as the solar resource filters down through the atmosphere, bouncing off of water droplets and vapor and pollution and whatnot, we lose about 366 watts in its journey down to sea level. Sidebar conversation, we also can enhance the watts per meter squared using reflective surfaces. When we get decent weather, we'll take a tour out onto the rooftop and take a look at what we have for solar on the rooftop. And we have a white roof surface, and this fall I was absolutely flabbergasted when we put the irradiance meter on the array at the same angle as the array, and the array was seeing 1,200 and some watts per meter squared. We had this additional 200 and some watts just from the reflective surface of the white roof. So we can enhance the performance of a system by landscaping or roofscaping. We have the three different types of irradiance. We have direct beam, we have albedo, which is reflection off of shiny surfaces like ice caps in the ocean, and then we have this diffuse radiation, which is absorbed into the clouds and then illuminates indirectly. We've talked about that before. I don't believe we've seen this before, peak sun hours. We've talked about sun hours. What they're talking about is this. So when the sun comes up, we get a little bit of a radiance and a little bit of watts per meter squared. And as time goes on, we get higher and higher performance and output of the system. And at some point, I don't know, roughly around perhaps 10 o'clock or so, till 2 o'clock, we'll get this peak performance, which is about 1,000 watts per meter squared. But I think a better way to think of this is at sunup, I'm going to take my irradiance meter and take a reading and start building a graph. Say it's 50 watts per meter squared. So I raise a bar vertically up to represent 50 watts per meter squared. 15 minutes later, I take another reading and say that's 100 watts per meter squared. Then I create a vertical bar that represents 100 watts per meter squared. Then another 15 minutes, I'm going to take another reading, and perhaps that's 200 watts per meter squared. So I draw a vertical line that represents 200 watts per meter squared, etc., etc., etc. I do that throughout the entire day, and we're going to call these lines bins or buckets of information. And as time goes on a clear day, we're going to get longer and longer lines representing more and more energy being produced at that particular moment. And so if we add that all up together, we get this cumulative peak sun hours, or we have an equivalent to, say, 4 sun hours per day, or 4,000 watt hours per day, kilowatt hours per day, cumulative. Or in the summertime, we could say over 6 hours we have 1,000 watts per meter squared, or 4 hours we have 4 hours of 1,000 watts per meter squared, and it's a cumulative over the course of the day. And we've seen this peak sun hours, or the average sun hours, I should say, when we messed around with PV watts and looked at the average sun hours for the year. Once again, here's the standard test conditions. If you don't know this, I would tattoo this onto your arm, someplace where it's readily available. 1,000 watts per meter squared, 1.5 air masses, and 25 degrees C at sea level. Now, that being said, we've been talking about this standard test condition. There's this other test conditions out there also. One of them is called PTC, or PV USA, which is not 1,000 watts per meter squared. It's I guess it is. I don't think that's accurate. PTC is 800 watts per meter squared, 25 degrees C, and then has a wind speed of 1 meter per second. And this is, that's strange. I'm going to dig into this a little bit. PTC is a standard that California uses. It's more of a real world performance of an array in heat, or a module in hot temperatures. So in summertime, when we're making our most energy, we're not going to get 1,000 watts per meter squared. We're going to get something like 800 watts per meter squared because of all the pollen and dust and water vapor in the atmosphere. Be aware that there's a thing called PTC and then STC. There's other things, NOC, which is another set of parameters, and SOC, which is another set of parameters. But this slide I don't think that's correct. I'll follow up on that with more information. We've seen this before. The zenith angle is directly overhead, and we can plot the course of the sun in degrees above the horizon, or elevation or altitude above the horizon, and then azimuth, which is degrees on the horizontal. Irradiance, we test irradiance with a pyranometer or irradiance meter. When you take your exam, when you see the word pyrometer, that's an irradiance meter. We're going to get those out as soon as we get a little bit of sunlight during class time. But nonetheless, when we take an irradiance meter, the meter collection window will be at the same plane as the array, so that the meter is seeing the same sun that the array is seeing. So as we saw um, with the PV watts, the tilt angle changes output, and orientation, the azimuth, changes performance as well. So we've already seen that. So our sweet spot for shading, or I'm sorry, sweet spot for um, production is this time period of um, 9 a.m. to 3 p.m. That's when we make 88% of our energy. If you look at the Solar Pathfinder chart, add up all the numbers between 9 in the morning to 3 in the afternoon, regardless of month, it always adds up to 88%. And then the shoulder times, before 9, after 3, we make energy too, but not of the same intensity. So shading is really critical. If we have some cells shaded, that might be okay. We can bypass around those shaded cell groups. But when shading cuts across the bottom side or each of the cell groups, then we lose complete power in that module. Here we have a module up on a rooftop. Here we have on the left a white um, plumbing vent. That's to vent your toilets and sinks so that the water will go down into the sewer. When there's full sun on the module, we have full electrical production on each cell that is connected together in series. When the sun starts shading the side of the module, we lose that cell group. And so these things called blocking diodes block off this cell group and reroute electrons around it. So it's like a detour. And so the module is still functioning, but it's lost 1/3 of its voltage output. And then if this shadow becomes greater, crossing over 2 cell groups, cell group 1, cell group 2, then 2 blocking diodes engage and reroute electrons around these high resistive shaded areas, and the module has now lost 2/3 of its potential voltage, but still functioning. We can, if we look at a large string of modules, we can mathematically calculate what the voltage should be, and then we can determine by some simple math how many thirds are in that array. We can detect by the voltage drop how many cell groups are missing by just taking one reading. It's really interesting how that works out. Back to our story, if I have shading that cuts across all 3 cell groups, this whole entire module is shut down. I talked briefly about a thing called magnetic declination. Not something that we have to really think about too much here in Illinois or Wisconsin, because the zero line for our compass goes roughly down through the Mississippi area from Minnesota down to the southern tip of Illinois, and then wanders off to the east. But nonetheless, we're about 2 degrees off from true north-south, this true north-south line. But if you're in Maine, if you're Jeff Ford moving to Maine, you're going to be 22 degrees, up to 22 degrees off from true south. So your magnetic compass has to be reset 22 degrees to compensate for that declination, or that difference between true magnetic north-south and true axial north-south. If you're over in the Cascades, you're going to be about 20 degrees off of true north-south. So magnetic north-south is different from polar north-south, and it depends on where you're located, and your compass will have to be adjusted for your location. Let's see. What else? Here's an installation going on. We have two distinct regions. We have the array, then we have the balance of systems. Balance of systems is everything but the array. That would include disconnects, inverters, breakers, service panel, AC disconnect, lightning protection, all that stuff. The BOS could be located in the house or it could be located outside the house. The company I work for, we try to get it in the building. Reason being that it's a controlled environment. It's not too wet, not too dry, not too cold, not too hot. And if I put it outside, then it's, even though these are rated for, our equipment is rated for being outside, like the inverters and disconnects and all that stuff is rated to be outside, but then it has greater swings of temperature, as low as 25 degrees, minus 25 degrees, to all the way up to 100 degrees Fahrenheit. And if it's in the sunlight, it's going to be even hotter on the south side of the building. Once we get those electronics over 122 degrees Fahrenheit, they start losing efficiency. So placing the balance of systems, namely the inverter, on the north side of the building keeps it cooler and more efficient. Let's see, what else? Next up, array configurations. So let me take a break, just a brief break right now. Okay, I'm back. You probably didn't even miss me. Anywho, some more review. We have a cell, and a group of cells make up a module. The correct term for this, the code term for this, is module. Even though in solar literature and when we talk, we call this sometimes a panel. It's not a panel. A collection of modules that are physically connected together is called a panel, and a collection of panels makes an array. So we could have a panel that is also an array, one panel making one array, or we could have multiple panels making an array too. We've talked about the construction of the module. We have hardened glass that's dimpled or acid etched to create edges in a prismatic effect to get more energy into the sun energy into the cells. The cells themselves are laid out and soldered together in series to make one great big giant chain. Each cell putting out approximately half a volt, and those are encapsulated in a polymer sheet. And then on the back side, there's a white or black back sheet called Tedlar. And then aluminum frame, which could be clear aluminum, or it could be black or bronze or some other color. I've seen yellow frames too, not yellow frames, orange frames, blaze orange frames. And they were for a project where in a remote location in another country where they were putting up modules during the daytime. They leave at night, come back in the morning, and all the modules were gone. So they made these orange framed modules so that they could run around town and collect their modules back up the next day. So that happens from time to time. Once again, we have light energy, wavelengths, or particles coming from the sun, penetrating the cell, knocking an electron out of its orbit. And if we have a wire connected to the top layer to an appliance, and then a wire to the bottom layer, we can have a flow of electrons. So the more perpendicular the rays of the sun are to the cell, the more energy we produce. The more cells we have, the more energy we produce, etc., etc. The upper layer, the end layer, is silicon that is impregnated with phosphorus gas. And then the bottom layer is the P layer, which is impregnated with gasified boron. So one has an abundance of electrons, one side has an absence of electrons. Let's see. We've seen this before too. I introduced the concept a few weeks ago, the IV curve. Over on the vertical axis at the very top we have ISC, or current short circuit. That's where when I plug the leads together I have maximum current, 0 voltage. This horizontal line is voltage. Here's the 0 mark right here in this corner. Once I engage that module or array, make it do work, then I have IMP, or current max power, and that would be at 1,000 watts per meter squared. On the vertical axis, 0 being on the left, maximum volts on the right, VOC, volts open circuit. That is when I have no connection to the module or array, and I read a voltage. That's maximum voltage, no current flow. Once I make that module or array do some work, I connect it to a load, then that voltage sinks down into VMP, or voltage max power. If I draw a line up from VMP to a curve and IMP over to the curve, this is called maximum power point at this point right here. That is the sweet spot, or maximum amount of power my module will put out under ideal conditions. But we know that we don't have ideal conditions all the time, meaning the sun is always shining 1,000 watts per meter square. So say we have half of that, or 500 watts per meter squared. The current line would be running across here horizontally to this point. And so then the inverter would apply more voltage, or allow more voltage into the system, so that we would be operating on this curve, further down the curve, but at its maximum power point for that given condition. This is also called the knee of the curve. Those are terms that you need to be familiar with for the exam that comes up at the end of the semester. The curve, the IV curve, is called fill factor. And so depending on how many volts we have, how many amps we have a region that's underneath that represents available power. Everything under this curve represents all the possibilities of output, power output, for a given voltage and a given current. Voltage is more or less going to be constant. It's current that's going to be changing. The current that changes is going to be changing due to clouds passing by, ice crystals in the air, time of day. All that stuff changes the current. It's going to be dynamic. We've seen this before. I want to skip over that. VOC, ISC. Here we go. So if we look at the IV curve, current is going to be variable. Voltage is more or less going to be constant. So as we change irradiance, down here we have 250 watts per meter squared, or about a quarter of the potential. At the very top we have 1,000 watts per meter squared, or the maximum potential. And then somewhere in between we have 500 and 700. So another way I could say is, if I have 25% sunlight, I'm going to get 25% output. If I have 50% sunlight, I'm going to get 50% output of that module, and so on and so forth. So current is the thing that affects the total output of the system. That's the variable. I haven't, let's see, here's another one with more ratings on it. And then they assigned current numbers to this with 0 all the way up to 3 amps. Voltage is going to be influenced by temperature, and this is going to be, and again, we're going to be more or less fixed at a fixed voltage. That's not going to vary very much. But know that this blue line is 25 degrees C, where my module is being tested. But when I raise the temperature to 50 degrees C, my voltage is going to go down significantly. As I decrease temperature, voltage is going to increase significantly. And that's what we're going to work on next week. We're going to run through temperature coefficient calculations to determine what is the maximum voltage, what is the minimum voltage of an array, a module or an array. And we're going to make strings. Here's some more temperatures. The higher the temperature, the lower the voltage. So in the summertime, well, standard test conditions is 25 degrees C or 77 degrees Fahrenheit, but what we're talking about is cell temperature, not ambient temperature. So and it's not uncommon to see a cell temperature of 140, 160, maybe even up to 180 degrees Fahrenheit. And that's really significant. Heat is resistance. So our voltage is going to go down. And our performance is going to go down. Our watts output will change. We started looking at module nameplates or data sheets. We'll be doing more of that in the future. I wanted to show you this. I don't think we've seen this before. This is the blocking diode concept. Here's one cell group. Here's another cell group. And then here are the blocking diodes on a possible detour route. So when things are operating normally, current is flowing from negative to positive through these wires right here, these pickups. When we have a shading, that's resistance. So in the first cell group, things are operating normal, running through the grid, hits the resistance, takes this alternate route. It can't go backwards because this is a blocking diode, can only go one direction. So current will take the path of least resistance and go through the bypass diode and continue on through the system. So these bypass diodes are things that can go that can malfunction from time to time. Now we have to take that module out of service and replace that module. And how often does that happen? I don't know. I've only seen it once or twice. It's not common to me, but on big systems, this may be a couple a year. On the back of modules, we have junction boxes. Old modules, we can actually get into there and do work, replace diodes. New junction boxes we may or may not be able to get into it, but it's going to be potted, or it's going to have an insulative material inside there encapsulating everything, so there's not much I can do with it. And nowadays we have these whips coming off of it, a positive and a negative lead, whereas back in the old days I've had to physically pipe and wire every connection. We've talked about series and parallel connections. We'll be dealing heavily with series connections coming up next week when we do our calculations. As we do series connections, positive to negative, current stays the same, voltage goes up. Parallel connections, when I connect positive to positive, negative to negative, current is additive, voltage remains the same. Here I have a series of modules, 1, 2, 3, 4, 5, 6, and each module is 22 22.5 volts and 5.75 amps. So as I connect positive to negative through the system, these 6 modules, it's cumulative for a grand total of 135 volts, 135, but current is equal to 1 module. It doesn't matter if I have 6 of these or 600 of these. Voltage increases, current will stay the same as 1 module. Of this array to the negative of this array to the negative of this array. The positives are connected at the ends, and the net result is that I have the voltage of a single string and the current of times 3. 1, 2, and 3. Here's another parallel connection. Each module is 24 volts, 10 amps. So the end result of these 4 small modules is that I still have 24 volts, but my current is 40 amps. So there's times when most of the time we're going to just be doing series connections. There are going to be times when we want to increase the current, or have the ability to increase the current, and we'll connect in parallel. It's not very common in the systems that I deal with on residential. I've done it once or twice on commercial systems. Let's see. All right. We're going to take a break right here, and I'm going to stop it, post this on what do we call that thing? Canvas. And then I'll make another recording of the next session. All right. This is just power curves, IV curves, for when we start paralleling devices together. So voltage stays the same, but current is going to be additive, so the current line is going to be taller. And then if it was in series, current would stay the same, but the VOC line would stretch out more horizontally. Okay, that's it, gang. Take a break, and I will have the next one up and posted. Hello, welcome to Lecture 2. It is now Thursday, yeah, and it's sunny and windy. Anyway, here we go. Inverters. Again, some of this stuff we've heard about, and some of this stuff we're going to drill down a little bit deeper. We need to understand the function of the inverter and the set points and things like that. Information we can find on the data sheet to help us build a string size. All right, inverters. So we have this DC signal coming from the solar array made up of modules, and that's going to be DC, straight line DC. Current is going to be variable, but voltage will be there all the time. So then at the inverter itself, to make it usable, we have to create a pure sine wave to integrate into the utility, or a modified sine wave, which is more choppy, which could be used for off-grid operations. Here's that. So the sine wave is this purely smooth wavelength, which we need for AC utility integration, or we could have this choppy, more blocky modified sine square wave, or modified sine wave. And these off-grid systems, work fine on modified sine. From my experience, we had buzzing in the stereo, and you couldn't charge up a battery for a battery drill. Hold on one second. It looks like the dog has to go out. Okay, crisis averted. We're back. Anyway, so we have these different waveforms, different availabilities. Most of the off-grid inverters are going to be true sine wave. It's the stuff that maybe you pick up at a truck stop or farmer and fleet or what have you. The small little ones that you're going to plug into a cigarette lighter could be or might be a modified sine. So in order to change this DC signal into an AC signal, we have to, the inverter is going to do is to use high-speed switching to turn on voltage and current and turn it off, turn it on, turn it off, turn it on, turn it off. They're going to use these pulses to simulate or build this bell curve, starting at the zero line up to a peak voltage, and then back down to the zero line and go in the opposite polarity, creating this sine wave. So this is called pulse width modulation, and it's this high-speed, high-frequency switching that is going to turn on and turn off for different periods of time, in milliseconds or microseconds, to build these waves. So when the pulses are wide, the current is on the most time, and then when they are narrower, indicates the least amount of current. So anyway, nonetheless, this high-speed switching creates this sine wave, this pure sine wave, which is actually better than utility-grade electrical. The voltages, we've talked about this before last week. We're limited to 600 volts DC for residential systems. We're limited to 1,000 volts DC for commercial systems. And then utility scale ground mounted systems can go up to 1,500 volts DC. So what this means is that I can have longer strings or more panels in series and maximize that voltage, and current stays the same. Volts times amps equals watts. So I can have more watts per string than, say, 600 volts. AC output, we're going to have 120, 240, 120, 208, 480, all sorts of different combinations are possible. And on the residential side, we have these smaller inverters. They have field selectable voltages. So depending on the application, whether it be single phase 120, 208, single phase 120, 240, whatever that might be, I program that AC voltage into the inverter, and it makes the connection. Microinverters, they're going to invert from low voltage DC into 240 volt AC right at the module, right at the microinverter. And so it's going to be running at 1 amp or thereabouts, maximum current, 240 volts, and then that microinverter just plugs into a cable, and there's roughly about 16 or so modules that are possible to make up a string, all connected together in series to make a total of 20 amps output. So that's the building blocks. Three-phase power, we can have inverters putting out three-phase AC as well, 60 hertz. But in this case, we're going to have three waveforms that are offset 120 degrees from each other. Standalone inverters, again, these have to be a inverter / charger so that I can hook a generator up to this inverter, and that will charge up the batteries if I don't have enough solar over a period of time. Grid interactive inverters, they're going to look for the AC signal from the utility and match that in its production. So this inverter is, say the grid is running at 240 volts, the inverter will put out around 241 or 242 volts to push back against the utility. So it's just a little bit more voltage, a volt or two, that allows it to push back and feed the loads inside the breaker panel. Any excess would push back against the utility through the meter. We have these DC to DC optimizers. Also, I would like to address those later when we actually set up a DC to DC optimizer based system. But nonetheless, that has a small device that is located behind the panel, and the panel will plug into the optimizer. Then the optimizers themselves will be connected in parallel with each other. Series with each other. So if one module goes out or something happens to a module, it doesn't impact the entire array. It just loses the production from that one module. The microinverters, again, those take the DC, put out usable AC, and these are becoming really popular. I think it's 90-some% of all systems that are installed are either optimizer based or microinverters, and the big players in that is SolarEdge for optimizer based systems, and then Enphase for microinverter systems. So one thing about these microinverters, it was a way for traditional electricians to get into the PV market without having to know a whole lot about solar. When you use a string inverter, there's you're working with DC, which is not intuitive to the walk-a-day AC electrician. So these microinverters putting out 240 volts AC right at the module, that was more intuitive. They understood AC electricity. You just hook up a two-wire branch circuit with a ground, and you're good to go. So that was in the early days, that was a way for electricians to get into the field without knowing a whole lot about it. As I said before, there are AC modules out there, and it's my opinion and observation that this is the death rattle of a module manufacturer. That's the last thing they do before they tank. And indeed, here we are with a Panasonic module. Panasonic made just incredibly great modules. We have some on the school. They really do good performance. But then they got in financial trouble and they started going to the AC module, and we don't see Panasonic modules anymore, unfortunately. This is the look on the left-hand side is a microinverter, the IQ7 from Enphase. And then on the right-hand side is the old, this is AP Solar. Oh, yeah. So there are a couple other players for microinverters, AP Smart being one of them. I have never seen one of those out in the field, as well as ABB. ABB produced, they bought Aurora, produced their own microinverters, and then somebody else bought them. Again, Enphase is almost the only kid on the block selling microinverters. That being said, that's not completely true. There's other players, but I don't know who they are. Here's a microinverter system, a block diagram. Or pictorial. Here we have the modules. Each module plugs into a microinverter, and then the microinverters are connected through a cord to the service panel. We can look at the performance of each individual module using power line communication to monitoring systems, and if one module is shaded or goes out, it's not affecting the performance of the whole system as a whole. So these are really nice for mediocre sites that have shading, like in the morning or afternoon. We have inverter nameplate ratings. Each data sheet for an inverter contains this information. We're going to have DC input information. Then we're going to have AC output information. This DC input information is what we're going to be looking for in our next step of calculations. And more on that next week. But what we want to know is, what is the MPPT voltage range? Here it is right here. If I can see that. So it looks like this is around 300 to 450 volts. So the inverter wants to see that voltage somewhere between 300 and 450 to make the inverter the most optimal it can be for the given conditions. So power output of an inverter, so we can have 5,000 watt inverters, 7,000s, 10,000s, 14s, whatever that might be. And it's not a standard increments of size. But however, there's a couple things that are unique to all of them. I can overload a 7,000 watt inverter to, say, 10,000 watts safely without damaging the equipment or being inefficient with the use of the array. There's calculations that we can do by hand, or we can enter them into a program, and it tells us what is the optimal string size to go into a particular inverter. And we're looking at the voltages, and then we're looking at the ultimate watt output. So here's our voltage ranges. We want to be running at voltages that are within the window of that MPPT operating voltage window for that inverter. And so that's the sweet spot we're aiming for in the summertime. We don't want to get voltage so low that it drops out. Maybe this is better. We don't want to get the voltage to drop so low that we lose our array. So at a certain point, if we lose our voltage because of heat, the inverter will shut down and then restart after it cools down. Cools down maybe, like in the afternoon. So we lose multiple hours of performance when the voltage sags too low. This isn't necessarily a problem for the Midwest, but it is a problem for California, Arizona, New Mexico, these down in the Sun Belt region. On the opposite end of that, we don't want to go beyond the voltage limitations of the inverter on cold days, and that's what we're concerned with in the upper Midwest. We don't want to have these voltages as they increase during the cold parts of the day. We don't want that to overvoltage our inverter, ultimately burning out the bus bar, and the manufacturer knows what that looks like. Overcurrent protection. This is an old way of doing it, where we have a circuit breaker for the DC coming in and the AC going out. Nowadays, that's an integrated switch. We have that DC disconnect and the AC disconnect to isolate this inverter. We run the DC conductors into the switch and the AC conductors out of it. And then if we have to replace the inverter, this inverter lifts off this wiring box, and then we put a new inverter on. None of the wiring from this wiring box is interrupted. It's either a knife connection, or there may be three conductors I may have to re-land, but it's not a big deal. I don't have to rewire everything into the inverter. But we are required to have this AC disconnect, which is going to be on the outside of the building